Hi guys, so doing the demonstration project, we're going to do the concept of rotational motion and how mass distribution affects the movement of rolling objects. So we have our hollow cylinder and our solid cylinder. They're going to roll down the slope. We have them with the same radius and they have the same mass as well. We're going to see the difference in their acceleration and their final speeds. And we should also take into consideration that the moment of inertia is more inwards with a solid cylinder and more outwards with our hollow cylinder. Let's do the experiment. I'm holding both of them and letting them go at the same time. So we can clearly see that the solid cylinder hit the bottom first. Tammy's going to explain more about why that exactly happens.
Okay, but why does this happen? Well, we already established it's the moments of inertia. As Anya explained, the solid cylinder has the mass directed more to the middle of it, and the hollow cylinder has the mass directed more to the outside of it. But what is moment of inertia? Well, moment of inertia is the measure of an object's ability to resist its change in rotational motion. At the top of the ramp, the solid cylinder converts more potential energy to translational kinetic energy rather than rotational energy, while the hollow cylinder converts more of the potential energy to rotational kinetic energy, resulting in the solid cylinder reaching the ground first. Thank you.
So in our demonstration, we saw how a solid cylinder rolls down faster than a hollow one because it has lower rotational inertia. The same principle applies in real life. First, in track cycling, athletes use solid disc wheels during the time trials, and this is because these wheels have most of their mass closer to the center, which means lower rotational inertia. As a result, they spin up more easily and reduce energy loss, helping cyclists maintain higher speeds. Secondly, we have Formula One cars which use ultra-lightweight wheels. This reduces the rotational inertia, allowing the wheels to accelerate and decelerate faster, which gives the car a better performance during quick starts, sudden stops, and sharp turns. And lastly, think about a mountain bike versus a road bike. Mountain bikes have heavier wheels where the mass is near the rims, which increases rotational inertia and helps the cyclist maintain more stability. But it also makes acceleration slower. Thus, road bikes use lighter wheels for fast acceleration because they have less rotational inertia. So just like in our demo, in real world designs, controlling rotational inertia is key to balancing speed, stability, and performance. However, we ran into a few pitfalls. The weight wasn't evenly distributed, and this caused the hollow can to roll unevenly, sometimes drifting to one side and wobbling and bumping against the sides of our track. As a result, the can would slow down or even veer off course, which interfered with the accuracy of our results. This unexpected behavior showed us how important it is to have cylinders with symmetrical and balanced mass distribution. So we revised our design and decided to 3D print our two cylinders, one solid and one hollow, with equal mass and radius. This change gave us better control over the internal mass distribution and made the experiment more reliable and fair. To conclude, our demonstration clearly showed that the solid cylinder consistently rolled down faster than the hollow one, even though they had the same mass and radius. This is due to the difference in rotational inertia, as the hollow cylinder has more of the mass further from the axis of rotation, so more energy goes into spinning the wheel rather than moving it further. This experiment helped us understand the deeper mechanics of rotational motion. It also highlighted the importance of careful design when testing physical principles, from mass distribution to surface smoothness, and many factors that can affect the outcome. In the end, our improved setup with 3D printed cylinders allowed us to clearly demonstrate the physics behind the rolling race. Thank you.